The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Actually, two things to say about eigenvalues. One is about matrices in general, and then the second is to focus on our favorites, those second derivatives and second differences. So there's a lot to say about eigenvalues, but then we'll have the main ideas. So the central idea, of course, is to find these special directions, and we expect to find n directions, n eigenvectors y, where this n by n matrix is acting like a number in each of those directions. And what we now want to do is, so that we have this for n different y's, and each one has its own eigenvalue lambda. And of course, the eig command in MATLAB will find the y's and the lambdas. Okay, so it finds the y's and the lambdas in a matrix. So that's what I'm going to do now. Straightforward. Anytime I have n vectors, so I have n of these y's, I have n y's and n lambdas. Well, if you give me n vectors, I put them into the columns of a matrix, almost without thinking. So can I just do that? So there's y1, the first eigenvector, this y2 to yn. Okay, that's my eigenvector matrix. Often I call it S. So I'll stick with that. S will be the eigenvector matrix. Okay, now, since these are eigenvectors, I'm going to multiply that matrix by A. That should bring out the key point. I'm just going to repeat this, which is one at a time, by doing them all at once. Okay, so what happens if I multiply a matrix by a bunch of columns? Matrix multiplication is wonderful. It does the right thing. It multiplies A times the first column. So let's put that there. A times the first column along to A times the last column. Just column by column. Okay, but now we recognize these. These are special y's. They're special because they're eigenvectors. So this is lambda 1y. 1 along to that column is lambda n y n, right? Okay? Just now I've used the fact that they were eigenvectors. And now one final neat step of matrix multiplication is to factor out this same eigenvector matrix again and realize, and I'll look at it, that it's being multiplied by this diagonal. That's now a diagonal matrix of eigenvalues. So let's just look at that very last step here. Here I had the first column was lambda 1 times y1. Okay, I just want to see, did I get that right? And in this, if I'm looking at the first column, where that lambda 1 is sitting, it's going to multiply y1 and it'll be all zeros below. So I'll have none of the other eigenvectors. So I'll have lambda 1 y1, just what I want. So it got a little squeezed near the end there. But so let me write above, the result is just A times this eigenvector matrix that I'm going to call S equals what? So this is A lambda equal AY equal lambda y for all n at once. A times S is, what have I got here? What's this? That's S. And what's the other guy? That's the eigenvalue matrix. So it's just got n numbers. They automatically go on the diagonal. And it gets called capital lambda. Capital lambda for the matrix, little lambda for the numbers. Okay, so this is n. This is all n at once. Straightforward. Okay. And I can, now I'm going to assume that I've got that these n eigenvectors, that I've been able to find n independent directions. And almost always you can For every symmetric matrix, you automatically can. So these y's are independent directions. If those are the columns of a matrix, yeah, here's a key question about matrices. What can I say about this matrix S if its n columns are independent? Whatever that, we haven't focused in careful detail, but we have an idea. That means, sort of, none of them are combinations of the others. We really have n separate directions. Then that matrix is invertible. It's a matrix that's got n columns independent. That's what we're hoping for. That matrix has an inverse. We can produce, well, it's all the good facts about matrices. This is a square matrix. So I can invert it, if you like, and I can write A as S lambda. I'm multiplying on the right by this S inverse. And there I have the diagonalization of a matrix. The matrix has been diagonalized. And what does that mean? Well, this is, of course, the diagonal that we're headed for. And what it means is that if I look at my matrix and I pay attention to separate out the different eigen directions, I could say, that the matrix in those directions is just this diagonal matrix. So that's a short way of saying it. Okay, so that's what you would, let me just carry one step further. And what would A squared be? Well, now that I have it in this cool form, S lambda S inverse, I would multiply two of those together. And what would I learn? If I do that multiplication, what comes out? First an S from here, and then what? Lambda squared. Why lambda squared? Because in the middle is the SS inverse that's giving the identity matrix. So then the lambda multiplies the lambda, and now here's S inverse. Well, A squared is S lambda squared S inverse. What does that tell me in words? That tells me that the eigenvectors of A squared are the same as for A. And it tells me that the eigenvalues of A squared are the squares of. So I could do this, maybe I did it before, one at a time. AY equal lambda y, multiply again by A squared y is lambda AY, but AY is lambda y, so I'm up to lambda squared y. It's just, you should just see that when you've got these directions, then your matrix is really simple. Effectively, it's a diagonal matrix in these good directions. So that just shows one way of seeing. And of course, what about A inverse? We might as well mention A inverse. Suppose A is invertible. Then what do I learn about A inverse? Can I just invert that? Suppose I take that. I'm just playing with that formula, so you'll kind of like get handy with it. What would the inverse be if I have three things in a row multiplied together? What's the inverse? So I'm going to take the inverses in the opposite order, right? So the inverse of that will come first. So what's that? Just S. The lambda in the middle gets inverted, and then the S at the left, its inverse comes at the right. Well, what do I learn from that? I learned that the eigenvector matrix for A inverse is same thing again, same. Let me put just same. What's the eigenvalue matrix for A inverse? It's the inverse of this guy, so what does it look like? It's got 1 over lambdas. That's all it says. So the eigenvalues for A inverse are just 1 over the eigenvalues for A. I mean, if that is so, and it can't be difficult, we could prove it sort of like one at a time. how would I get from this? This is my starting point always. How would I get to A inverse now and recover this fact that the eigenvalues are for the inverse are just turn them up. If A has an eigenvalue 7, A inverse will have an eigenvalue 1/7. And let's just, what do I do? We usually multiply both sides by something sensible, right? That's, what shall I multiply both sides by? A inverse sounds like a good idea, right? A inverse is, so I'm multiplying both sides by A inverse, so that just leaves y, and here's that number, and here's A inverse times y. Well, maybe I should do one more thing. What else shall I do? Divide by lambda. Take that number lambda and put it over here as 1 over lambda. Well, just exactly what we were looking for. The same y has A inverse as the same y as an eigenvector of A inverse, and the eigenvalue is 1 over lambda. Oh, and of course, I should have said, before I inverted anything, what should I have said about the lambdas? Not 0, right? A 0 eigenvalue is a signal the matrix isn't invertible. So that's perfect test. If the matrix is invertible, all its eigenvalues are not 0. If it's singular, it's got a 0 eigenvalue. If a matrix is singular, then AY would be 0y there'd be a vector that matrix kills. If A is not invertible, there's a reason for it. It's because it takes some vector to 0, and of course you can't bring it back to life. So lambda equals, so I just put that up here. Lambda equals 0 would tell me I have a singular matrix. All lambda not equal 0 would tell me I have an invertible matrix. Okay. So these are straightforward facts. It's taken down in this row, and it's just really handy to have up here. Okay. Well, now I'm ready to move toward the specific matrices, our favorites. Now, those are symmetric. So maybe before I leave this picture, we better recall what is special when the matrix is symmetric. So that's going to be the next thing. So if A is symmetric, I get some extra good things. So let me take, instead of A, I'll use K. So that'll be my letter for the best matrices. So symmetric. Okay. So now what's the deal with symmetric matrices? The eigenvalues, the lambdas, I'll just call them the lambdas and the y's. The lambdas are, do you remember from last time, if I have a symmetric matrix, the eigenvalues are all, anybody remember? They're all real numbers. You can never run into complex eigenvalues if you start with a symmetric matrix. We didn't prove that, but it's just a few steps like those. And what about, most important, what about the y's, the eigenvectors? They are, or can be chosen to be, or whatever. Anybody remember that fact? So these are like the golden facts. Every sort of bunch of matrices reveals itself through what its eigenvalues are like and what its eigenvectors are like. And the most important class is symmetric, and that reveals itself through real eigenvalues and orthogonal. Good. Orthogonal eigenvectors. Orthogonal. And in fact, since I'm an eigenvector, I can adjust its length as I like, right? If y is an eigenvector, 11y is an eigenvector, because I would just multiply both sides by 11. That whole line of eigenvectors is getting stretched by lambda. So what I want to do is make them unit vectors. MATLAB will automatically produce, if Eig would automatically give you vectors that have been normalized to unity. In other words, What does that, let me put down, yeah, here's something good. So what does orthogonal mean? That means that one of them, the dot product of one of them with another one is, now that's not I didn't do the dot product yet. What symbol do I have to write on the left-hand side to, well, you could say just put a dot, of course. But dots are not cool, right? I mean, so maybe I should say inner product. That's the more kind of upper class word. But I want to use transpose. Yeah, so it's the transpose. That's the dot product. And that's the test for perpendicular. So what's the answer then? I get a 0 if I is different from j. If I'm taking two different eigenvectors and I take their dot product, that's what you told me they're orthogonal. And now what if I equals j? If I'm taking the dot product with itself, each eigenvector with itself. So what does the dot product of a vector with itself give? 1. It'll be 1 because I've normalized. Exactly. Yeah. What it always gives, the dot product of a vector with itself, you just realize that that'll be y1 squared, y2 squared. It'll be the length squared. And here we're making the length to be 1. Okay, now something, well, once again, if I write something down like this, which is straightforward, I want to express it as a matrix statement. So I want to multiply. It'll involve my good eigenvector matrix. And this will be what? So I want to take all these dot products at once. I want to take the dot product of every y with every other y. Well, here you go. Just put these guys in the rows. Now that we see that it really was the transpose multiplying y, do you see that that's just done it? In fact, you'll tell me what the answer is here. Don't shout it out, but let's take it 2 or 3 entries, and then you can shout it out. Okay, so what's the 1, 1 entry here of, this is, I guess that's what we called S, and now this would be its transpose. And what I'm saying is if I take, yeah, this is important because throughout this course we're going to be taking A transpose A, S transpose S, Q transpose Q, often. So here we got the first time at it. So what do I get? Why did I put a 0 there? Because it's not it. What is it? What is that first entry? 1. Because that's the row times the column. It's a 1. And what's the entry next to it? 0, right? y1 dot product with y2 is, we're saying 0. So what matrix have I got here? Yeah, I've got the identity, because y2, with y2, we'll put a 1 there, and all zeros elsewhere, 0, 0, and y3 times y3 will be the 1. I get the identity. So this is for symmetric matrices. We've in general, we can't expect the eigenvectors to be orthogonal. It's these special ones that are. But they're so important that we notice. Okay, now, so this is the eigenvector matrix, S, and this is its transpose. So I'm saying that for a symmetric matrix, S transpose times S is I. Well, that's pretty important. In fact, that's important enough that I'm going to give an extra name to S, the eigenvector matrix, when it comes from a symmetric matrix, when it has a matrix with S transpose times S equaling the identity, is really a good matrix to know. And let's just focus on those guys. Okay, I can put that up here. So here's a matrix. Now, can I introduce a different letter than S? It just helps you to remember that this remarkable property is in force, that we've got it. So I'm going to call it, so for when K is a symmetric matrix, I'll just repeat that, then its eigenvector matrix has this S transpose times S. I'm going to call it Q. I'm going to call the eigenvectors, so for this special situation, A times, well, maybe I'll just leave it. So I'm going to call the eigenvector matrix Q. It's the S, but it's worth giving it this special notation to remind us that this is, so Q is an orthogonal matrix. There's a name for matrices with this important property. And there's a letter Q that everybody uses, an orthogonal matrix. And what does that mean? It means just what we said, Q transpose times Q is I. What I've done here is just introducing a special letter Q, a special name, orthogonal matrix, for what we found for eigenvectors of a symmetric matrix. And this tells me one thing more. Look what's happening here. Q transpose times Q is giving the identity. What does that tell me about the inverse of Q? That tells me, here, some matrix is multiplying Q and giving I. So what is this matrix? What's another name for this Q transpose? Is also Q inverse, because that's what defines the inverse matrix, that times Q should give I. So Q transpose is Q inverse. Okay. Okay, good. I'm moving along here. Yes, please. Yes? Yes. The question was, shouldn't I call it an orthonormal matrix? The answer is yes, I should. But nobody does. Damn it. So I'm stuck with that name. But orthonormal is the proper name. If you call it an orthonormal matrix, I'm happy, because that's really the right name for that matrix, orthonormal, because orthogonal would just mean orthogonal columns, but we've taken this extra little step to make all the lengths 1. And then that gives us this great property. Q transpose is Q inverse. Orthogonal matrices are like rotations. I better give an example of an orthogonal matrix. I'll do it right under here. Here's an orthogonal matrix. So what's the point? It's supposed to be a unit vector in the first column, so I'll put cos theta sine theta. And now what can go in the second column of this orthogonal matrix? It's got to be a unit vector again, because we've normalized. And it's got to be, what's the connection to the first column? Orthogonal. Got to be orthogonal. So I just want to put something here that sum of squares is 1, so I'll think cos theta and sine theta again. But then I've got to flip them a little to make it orthogonal to this. So if I put minus sine theta there and plus cos theta there, that certainly has length 1. Good. And the dot product, can you do the dot product of that column with that column? It's minus sine cosine plus sine cosine 0. Yeah, so there is a 2 by 2. Actually, that's a fantastic building block out of which you could build many orthogonal matrices of all sizes. That's a rotation by theta. That's a useful matrix to know. It takes every vector, swings it around by an angle theta. What do I mean? I mean that Q times a vector x rotates x by theta. Let me put it. qx rotates whatever vector x you give it. You multiply by q. It rotates it around by theta. It doesn't change the length. And so that would be an eigenvector matrix of a pretty typical 2 by 2. Okay. All right. I see as I talk about eigenvectors, eigenvalues, there's so much to say. Because everything you know about a matrix shows up somehow in its eigenvectors and eigenvalues. And we're focusing on symmetric guys. So what do we have finally? What happens to this A equal S lambda S inverse? Let's write that again. Now we've got K. Okay, it's S lambda S inverse, like any good diagonalization. But now I'm giving S a new name, which is what? Q. Because when I give K, when I use that letter K, I'm thinking symmetric. So I'm in this special situation of symmetric. I have the lambda, the eigenvalue matrix, and here I have Q inverse. Okay, but there's another little way to write it, and it's terrifically important in mechanics, in dynamics, everywhere. It's simple now. We know everything. Q lambda what? Q transpose. That, do you see the beauty of that form? That's called the principal axis theorem in mechanics. It's called the spectral theorem in mathematics. It's diagonalization. It's quantum mechanics. Everything. Anytime you have a symmetric matrix, there's the wonderful statement of what that matrix how it breaks up when you look at its orthonormal eigenvectors and its real eigenvalues, and you see that once again the symmetry has reappeared in the three factors. The symmetry has reappeared in the fact that this factor is the transpose of this one. We saw that for elimination when these were triangular. You remember, just to remember what that makes me remember what we had in a different context. In the elimination, when things were triangular, we had K equal LD L transpose. I just squeezed that in to ask you to sort of think of the two as two wonderful pieces of linear algebra in such a perfect shorthand, perfect notation. This was triangular times the pivot matrix times the upper triangular. This is orthogonal times the eigenvalue matrix times its transpose. And the key point here was triangular, and the key point here is orthogonal. Okay. Well, that took some time, but it had to be done. This is the right way to understand. That's the essential thing. That's a highlight of a linear algebra course, and we just went straight to it. And now what I wanted to do was look now at the special K. Oh, that's an awful pun, but okay. So at the special matrices that we have, can we? So those are n by n, and as I said last time, usually it's not very likely that we find all the eigenvalues and eigenvectors of this family of bigger and bigger matrices. Of course, you're all remembering. So now I'm going to specialize to my n by n matrix. K equals, 2's down the diagonal, minus 1's above, and minus 1's below. Okay. What are the eigenvalues of that matrix, and what are the eigenvectors? All right. How to tackle that? The best way is the way we've done with the inverse and other ways of understanding K, was to compare it with the continuous problem. So this is a big matrix which is a second difference matrix, fixed. Everybody remembers that the boundary conditions associated with this are fixed. I want to look, or ask you to look at the corresponding differential equation. So you may not have thought about eigenvectors of differential equations. And maybe I have to call them eigenfunctions, but the idea doesn't change one bit. So what shall I look at? K corresponds to what continuous differential business, what derivative, what? So I'm looking, I would like to look at ky equal lambda y, but I'm looking for the y's and lambdas, and the way I'm going to get them is to look at the, what did you say it was? K, now I'm going to write down a differential equation that's like this, but we'll solve it quickly. So what will it be? K is like, tell me again, second derivative. So second derivative of y with respect to x squared. And there's one more thing you have to remember, minus. And here we have lambda times y of x. That's an eigenvalue and an eigenfunction that we're looking at for this differential equation. Okay. Now, there's another thing you have to remember, and you'll know what it is, and you'll tell me. There's more. I could look for all the solutions. Well, let me momentarily do that. What functions have second derivative minus the second derivative is a multiple of the function? Can you just tell me a few? Because sine and cosine. I mean, this is a fantastic eigenvalue problem because its solutions are sines, and cosines. And of course, we could combine them into exponentials. So we could have, say, sine omega x, or cos omega x, or we could combine those into e to the I omega x, would be a combination of those, or e to the minus I omega x. Those are combinations of these, so those are not new. Okay. We got lots of eigenfunctions. Oh, for every frequency omega, this solves the equation. And what's the eigenvalue? If you guess the eigenfunction, you got the eigenvalue just by seeing what happens. So what would the eigenvalue be? Yeah, tell me again. Omega squared. Because I take the second derivative of the sine, that would give me the cosine, back to the sine, omega squared comes out, omega comes out twice. Oh, it comes out with a minus sign from the cosine, and that minus sign is just right to make it plus. Lambda is omega squared. So omega squared, all the way, of course. Those are the eigenvalues. Now, all our differential equation examples had something more than just the differential equation. What's the additional thing? That a differential equation comes with boundary conditions. With boundary conditions. Otherwise, we got too many. I mean, we don't want all of these guys. So what boundary conditions are, if we're thinking about K, our boundary conditions should be fixed and fixed. So that's the full problem. This is part of the problem, not just an afterthought. Okay, now, these conditions, that will be perfect. Instead of having all these sines and cosines, we're going to narrow down to a family that satisfies the boundary conditions. Okay. First boundary condition is it has to be 0 at x equals 0. What does that eliminate now? Cosines are gone. Keeps the sines. Cosines are gone by that first boundary condition. These are the guys that are left. All right. Yeah. I won't deal with these at this point because I'm down to signs already from one boundary condition. And now the other boundary condition. So now I have, the other boundary condition is, at x equal 1, I get sine, if it's going to work, sine of omega x has to be, no, what do I put now? Sine of omega, right? X is 1. I'm plugging in here. I'm just plugging in x equal 1 to satisfy, and it has to equal 0. So that means that pins down omega. Doesn't give me just 1 omega. Well, tell me 1 omega that's okay then. The first omega that occurs to you is pi. The sign comes back to pi. So we've got 1. Why 1? Our first guy is, with omega equal pi, is sine of pi x. Right. That's our fundamental mode. That's the number 1 eigenfunction, right? And it is an eigenfunction. It satisfies the boundary condition. Everybody would know its picture, just one arch of the sine function. And the lambda that goes with it, lambda 1. So this is the first eigenfunction. What's the first eigenvalue? Pi squared, right? Because omega we took to be pi. So lambda 1 is pi squared. Good. We've got one. We were able to do it because we could solve this equation so in an easy way. Now, ready for a second one. What will the next one be? The next eigenfunction, it's got to, whatever its frequency is, omega, it's got to have sine of omega equals 0. What's your choice? 2 pi. So the next one is going to be sine of 2 pi x. And what will be the eigenvalue that goes with that guy? Lambda 2 will be omega squared, which is 2 pi squared, 2 pi all squared, so that's 4 pi squared. You see the whole list. The signs with these correct frequencies are the eigenfunctions of the second derivative with fixed boundary conditions. And this is entirely typical. We don't have just n of them. The list goes on forever, right? List goes on forever because we're talking here about a differential equation. That's a differential equation somehow like a matrix of infinite size. And somehow these signs are the columns of the infinite size eigenvector matrix. And these numbers, pi squared, 4 pi squared, 9 pi squared, 16 pi squared, are the eigenvalues of the infinite eigenvalue matrix. Okay, we got those answers quickly. And let's just mention that if I change to free fixed or to free, I could repeat. I'd get different y's. If I have different boundary conditions, I expect to get different y's. In fact, what would it look like if I had if that was y prime equals 0 as the left end? So what would you expect the eigenfunctions to look like? They'd be cosines. They'd be cosines. And then we would have to adjust the omegas to make them come out right at the right-hand end. Yeah, so this y of 0 equals 0, the fixed ones gave us sines. The free ones give us cosines. The periodic ones, if I had y of 0 equal y of 1, so that I'm just circling around, then I would expect these e to the I kx's. The textbook will, so I'm in the eigenvalue section, of course, and the textbook lists the answers for the other possibilities. Let's go with this one, because this is the one that corresponds to k. All right. Finally, okay, we're now ready for the the final moment, and it is, can we guess the eigenvectors for the matrix? Now I'm going back to the matrix question. And as I say, normally the answer is no. Who could guess? But you can always hope. You can try. And so what will I try? I'll try, here, let me draw sine x, sine pi x. And let me remember that my matrix K was a finite difference matrix. It came from, let's make it 4 by 4. 1, 2, 3, 4, let's say. And what would be the best I could hope for the eigenvector? The first eigenvector, I'm hoping that the first eigenvector of K is very, very like the first eigenfunction in the differential equation, which was this sine pi x. So that's sine pi x. Well, what do you hope for? What shall I hope for as the components of y1, the first eigenvector? It's almost too good. And as far as I know, basically it only happens with these sines and cosines example. These heights, I just pick these, what I might call samples of the thing. Those 4 values, and of course, 0 at that end and 0 at that end. So because K, the matrix K is building in the fixed. These 4 heights, these 4 numbers, those 4 signs, in other words, what I hope is that for ky equal lambda y, I hope that y1, the first eigenvector, it'll be sine pi x, but now what is x? So this is x here, from 0 to 1. So what's x there, there, and there? Instead of sine pi x, the whole curve, I'm picking out those 4 samples. So it'll be it'll be the sine of, what will it be here? Pi divided by n plus 1, which in my picture would be, we'll make it completely explicit, 5. It's 1/5 the way along. Maybe I should make these y's into column vectors since we're thinking of them as columns. So here's y1, sine pi over 5, sine 2 pi over 5, sine 3 pi over 5, sine 4 pi over 5. That's the first eigenvector. And it works. And you could tell me you could guess now the general one. Oh, well, when I say it works, I haven't checked that it works. I'll better do that. But the essential point is that it works. Okay. Yeah. I may not even do it today. Okay. So in fact, tell me the second eigenvector. Oh, tell me the second eigenfunction over here. What's the second eigenfunction? Let me draw it with this green chalk. So I'm going to draw y2. And now what does y2 look like? Sine 2 pi x. What's the new picture here? It goes up. What does it do? By here it's got back. Oh no. Damn. Okay. I would have been better with 3 points in the middle, but it's correct. It comes down here, right? That's sine 2 pi x. That's halfway along. Oh, now, okay. Huh. Yes, and I'll finish this guy. This will be sine of 2 pi over 5, sine of 4 pi over 5, See, I'm sampling this same thing. I'm sampling 2 pi x at those same points, sine of 6 pi over 5 and sine of 8 pi over 5. Just maybe let's accept this as correct. It really works. It's the next eigenvector. And then there's a third one, and then there's a fourth one. And how many are there? N, usually. And in my case, what is n in the picture I've drawn? N is, here is 4. 1, 2, 3, 4. N is 4 in that picture. And that means that I'm dividing by n plus 1, because this is the same as, that's really sine of pi h. You remember I used h as the step size? So h is 1/5, 1 over n plus 1, 1/5. Yeah. So it's sine pi h, sine 2 pi h, 4 pi h, 3 pi h, 4 pi h. Here's 2, sine 2 pi h, sine 4 pi h, sine 6 pi h, sine 8 pi h. Okay. So I have 2 things to do. One is to remember what is the remarkable property of these y's. So there's a y that we've guessed. Right now you're taking my word for it that it is the eigenvector, and this is the next one. I copied them out of those functions. And just remind me, what is it that I'm claiming to be true about y1 and y2? They are orthogonal. They're orthogonal. Well, okay, to check that, I'd have to do some trig stuff. But what I was going to do was come over here and say, this was a symmetric differential equation. We found its eigenfunctions. What do you think's up with those? Those are orthogonal too. So this would be a key fact in any sort of advanced applied math, is that the sine function is orthogonal to the sine 2x. That function is orthogonal to this one. And actually, that's what makes the whole world of Fourier series work. So that was really a wonderful fact, that this is orthogonal to this. Now you may quite reasonably ask, what do I mean by that? What does it mean for 2 functions to be orthogonal? Why don't we just, as long as we're getting all these parallels, let's get that one too. I claim that this function, which is this, is orthogonal to this function. Okay, what does that mean? What should these functions, could I write dot or transpose or something? But now I'm doing it for functions. I just want you to see the complete analogy. So for vectors, what did I do? If I take a dot product, I multiply the first component times the first component, second component times the second, so on and so on. Now, what will I do for functions? I multiply sine pi x times sine 2 pi x at each x. Of course, I've got a whole range of x's. And then what do? I integrate. I can't add. I integrate instead. So so I integrate one function, sine pi x, against the other function, sine 2 pi x dx. And I integrate from 0 to 1. And the answer comes out 0. The answer comes out 0. The sine functions are orthogonal. The sines are orthogonal functions. The sine vectors are orthogonal vectors. I normalize to length 1, and they go right into my Q. So if I did that times that dot product would turn out to be 0. If I had been a little less ambitious and taken n to be 2 or 3 or something, we would have seen it completely. But maybe doing with 4 is okay. Well, so great lecture except for that. Didn't get there. Okay, so next, so Wednesday's lecture is sort of the bringing all these pieces together, positive eigenvalues, positive pivots, positive definite. So come on Wednesday, please. Come Wednesday. Okay, and Wednesday afternoon I'll have the review session as usual.